Good afternoon. My name is Kavya Rajesh and I am here to take a small portion of the autocorrelation. As we all know about the autocorrelation, however, in cross-section studies, data are often collected on the basis of a random sample of cross-sectional unit, such as households, for example, in a consumption function analysis, or firms in an investment study analysis, etc. So that there is no prior reason to believe that the error term pertaining to one household or firm is correlated with an error term of another household or firm. If by chance such a correlation is observed in cross-section unit, it is called spatial autocorrelation, that is, correlation in space rather than over time. However, it is important to remember that in cross-section analysis, the ordering of the data must have some logic or economic interest to make sense of any determination of whether autocorrelation is present or not. The situation, however, is likely to be very difficult if you are dealing with time series data. For the observations in such data follows a natural ordering over time so that successive observations are likely to exhibit intercorrelations, especially if the time interval between successive observations is short, such as a day, a week, or a month rather than a year. If you observe stock price indexes such as Dow Jones or S&P 500 over successive days, it is not unusual to find that these index move up or down for several days in succession. Obviously, in situations like this, the assumption of non-auto or serial correlation in the error term that underlies the CLRM will be violated. Next, we can look into the nature of the problems of autocorrelation. The term autocorrelation may be defined as a correlation between members of series of observation ordered in time. That means as in time series data or space as in cross-section data. In the regression context, the classical linear regression model assumes that such autocorrelation does not exist in the disturbance Ui. Symbolically, Ui Uj divided by xi and xj equal to E bracket ui and uj bracket close equal to 0, that is I not equal to j. Put simply, the classical model assumed that the disturbance term relating to any observation is not influenced by the disturbance term relating to any other observation. For example, if you are dealing with quarterly time series data involving the regression of output on labor and capital input, and if say there is a labor strike affecting output in one quarter, there is no reason to believe that this disruption will be carried over to the next quarter. That is, if output is lower this quarter, there is no reason to expect it to lower next quarter. Similarly, if we are dealing with cross-sectional data involving the regression of family consumption expenditure on family income, the effect of an increase of one family's income on its consumption expenditure is not expected to affect the consumption expenditure of another family. However, if there is such a dependence, we have autocorrelation symbolically E bracket ui uj bracket close and not equal to 0, that means I not equal to j. In this situation, the disruption caused by a strike this quarter may very well affect output next quarter, or the increase in the consumption expenditure of one family may very well prompt another family to increase its consumption expenditure if he wants to keep up sum by 3. This averaging introduces smoothness into the data by dampening the fluctuations in the monthly data. Therefore, the graph plotting the quarterly data looks much smoother than the monthly data, and this smoothness may itself lead to the systematic pattern in the disturbance, thereby introducing autocorrelation, another source of manipulation in interpolation or extrapolation of data. For example, the census of population is conducted every 10 years in this country, the last being in 2000 and the one before that in 1990. Now, if there is a need to obtain data for some year within the interval period 1990-2000, the common practice is to interpolate on the basis of some ad hoc assumption. All such data massaging techniques might impose upon the data a systematic pattern that might not exist in the original data. And the last second one is data transformation. As an example of this, consider the following model that yt equal to beta 1 plus beta 2 xt plus ut, and the yt minus 1 equal to beta 1 plus beta 2 xt minus 1 plus ut minus 1, where yt minus 1, xt minus 1 and ut minus 1 are known as lagged values of y, x and u respectively, here lagged by one period, where delta, known as the first difference operator, tell us to take successive difference or the variables in the question. Thus, delta yt is equal to yt minus 1, comma delta xt is equal to xt minus 1 and delta ut equal to ut minus 1. And the last one is non-stationarity. While dealing with time series data, we may have to find out a given time series in a stationary. Also, we will discuss the topic of non-stationary time series more thoroughly in the loosely speaking, a time series is stationary. If its characteristics, example mean, variance and covariance are time invariant. That is, they do not change over time.